So for my project, I worked with some adversarial search on Connect 4, and I used a few different techniques that I'm going to talk about. Okay, so here is the engine I wrote for Connect 4. It's a simple text-based UI, and basically what you do is you just enter the column you want to drop a tile in. And right now I just am playing with two human agents, so I'm just placing all the tiles, and you can see what happens is that the tiles get dropped. Ones are for the first player, twos are for the second player, and then if you get 4 in a row, it'll declare a winner and you can restart the game. So there's a few things I wanted to do. I wanted to compare a few different agents that were implemented in different ways and also find some techniques to improve them. The information gained from these agents can make an agent that is reasonably fast, does some positional moves potentially, and cannot be beaten too easily in either a different Connect 4 game, or if I wanted to improve the UI of my Connect 4 game on a more widespread application. Another thing is that some of the knowledge from these agents could be transferred to other games. My first implementation of the agent was just a simple minimax tree-searching algorithm with alpha-beta pruning. It also had an evaluation function. So I'm going to go ahead and give you an example of my agent at depth 3. If you watch, I'll make a move and then it'll decide on the best move based on its heuristic and its searching algorithm. It seems to make pretty reasonable moves most of the time. However, there's a few things about it not choosing very positional moves, like choosing a more central column early in the game. So that's definitely something that I could work on if I was to work on the heuristic more. One thing that I didn't love about this AI is that once I entered apply of 4, it started to slow down to where it wasn't really fun to play against anymore. I think this was a combination of the game being stored as a 2D array and it having to be copied every single time that the AI generated a successor, and also the fact that each time the evaluation function ran, it basically passed through the entire 2D array 4 times. Overall, this meant that I couldn't really make the AI stronger with this implementation, other than improving the heuristic to make better moves. One method I tried to implement that would basically increase the speed at deeper applies was the idea of bitboards. Basically, what you do is you store the entire state of the game in a series of bits. I'll go into more detail on how this works in a second. In general, though, it allows you to store basically the state of the game in a much smaller data structure, and also, if you can do bitwise operations to learn certain features about the game, you can perform calculations on it much quicker. So if you look at the rightmost bit for the first player, that basically represents the bottom square of the leftmost column of the Connect 4 board. And then if you look at the second player, that's the square right on top of that. There's a few other methods I used for improving the algorithm. One is simplified pruning. Since there's only 3 values in the algorithm without the heuristic, I don't need to store as much data for alpha-beta pruning. The other thing is that the exploration order. So since Connect 4, the best moves are normally in the center, exploring the center nodes made the pruning more effective. So I decided to rewrite the algorithm in C++ to take advantage of the bit vectors in there, because the bit vectors in Python are not very efficient. Here's an example of it running at depth 4 once I have everything I talked about implemented. Here's a comparison of the 3 different implementations I had when I was done. As you can see that once I switched to C++ with the enhancements, it got quite a bit faster than the other 2 implementations. Understanding how you're going to implement your ideas in an efficient way is important. I learned that in Python, the bit vector class I was using is actually pretty inefficient, and I wasted a lot of effort trying to get it to work when in reality it didn't even improve my speed almost at all. I also found that in the domain of Connect 4, going deeper in the search tree seemed to do a lot better at what I wanted it to do than staying at a lower depth and trying to mess with the heuristic more.